So today's topic is about rotational inertia. Okay, so before I talk about rotational inertia, I want to kind of review what we have learned in terms of linear motion, because this chapter will focus on rotational motion, which is a little bit different from what we talked about before. But there are a lot of similarities between linear motion and rotational motion, how we represent those two kinds of motions. Okay, so remember, this is what we have covered, okay, for linear motion. Okay, so we talk about distance, right, in our class. We don't use displacement, we talk about distance. We talk about velocity, we talk about the acceleration, we talk about the mass, we talk about force, and also we discuss about kinetic energy and momentum. Okay, so similarly in rotational motion, so last video I kind of introduced that we have to use two kinds of speed to represent rotational motion. One is called tangential speed, which is very similar to the speed definition over here for linear motion, but the other one is actually called angular speed. So in rotational motion, we have some similar quantities that we can use to describe rotational motion to the ones actually used to describe linear motion. So in linear motion, we have displacement or distance, but in rotational motion, we use angle to represent displacement. So we call it angular displacement. We have linear speed, we have angular speed. We have acceleration, we have angular acceleration. So angular acceleration is trying to describe how the rotational speed is changing. Okay, either it's going to change in faster or it's going to change in slower. So it's very similar to the concept of acceleration. The acceleration is the rate of the change of velocity. And then we talk about the mass, right? Mass, and also actually mass is related to inertia of the object, right? So the greater the mass, the greater inertia. So inertia is the laziness of the object. It's going to be related to the property that how hard it's going to change the object's motion status. And then we have, similarly, we have in rotational motion, we have rotational inertia. We use I, capital I, to represent it. So this is called rotational inertia. So that's the thing we're going to talk about today. Okay. And then we have force. We learned about force equals mass times the acceleration, which is Newton's second law. But in rotational motion, we are going to introduce the concept of torque. So the torque we're going to talk about next class. So the torque not only depends on the force, but also depends on where you're applying the force. I'm going to introduce that in more details next class. But similarly, in rotational motion, we have Newton's second law too. So mass actually is replaced by inertia, rotational inertia. The acceleration is replaced by angular acceleration. So this becomes Newton's second law in rotational motion. Kinetic energy. Okay, kinetic energy definition is 1/2 mv squared, and then we have rotational kinetic energy. So you guys can guess, m is going to be replaced by I, v is going to be replaced by omega. So we have rotational kinetic energy definition. Momentum. Okay, so the momentum actually is, we have angular momentum. The angular momentum definition is we replace m by I and we replace v by omega. So that's going to be our definition of angular momentum. So we're going to cover all these things later. Focus on rotational inertia today. Next class, we're going to talk about torque. And then the following class, we're going to talk about momentum. Okay. So once you understand this, actually rotational motion, is not so hard to understand if we know what we learned before, and then you can see the analogy between the linear motion and rotational motion from this table here. So what I want to focus today is the concept of rotational inertia. If you can take a look at this slide here, okay. So an object rotating about an axis, which we call a rotational axis, tends to remain rotating about the same axis at the same rotational speed, unless interfered with by some external influence. Okay, so that's the thing we're going to talk about later. Okay. The property of an object to resist changes in its rotational state of motion is called rotational inertia. Okay, so remember, I wanted to go back to inertia again. So the inertia is the property of an object to resist changes in its linear state of motion. So initially the object is rest, so it's going to be harder to change from rest to motion. Or if something is moving, then it's going to be harder to change. It's going to resist that change from motion to be at rest. So similarly, rotational inertia here is the property of an object to resist changes in its rotational state of motion. If something is rotating, in rotational inertia is going to resist the change to not rotating. If something is at rest, the rotational inertia is going to resist the change, is going to resist to change, to be moving. Okay, so very similar to the concept of the inertia. Okay, so now, in other words, bodies that are rotating tend to remain rotating, while non-rotating bodies tend to remain non-rotating. So if something is at rest, it's going to try to be at rest. If something's rotating, it's going to be trying to be rotating because of rotational inertia. But rotational inertia, okay, is different from inertia because when we talk about rotation, sometimes we have to consider the shape of the object, okay, especially if you look at this slide here, okay, the rotational inertia depends on not only on the mass of the object, but also on how the mass is distributed around the axis of rotation. So if you look at these two examples here, so you see here, this is going to be much easier to rotate than this one, okay? Because the greater the distance between the object's mass concentration and the axis, the greater the rotational inertia is going to be. So when something has greater mass, it's going to have greater rotational inertia. But when the distribution of the mass is further away, or the mass is further away from the axis of rotation, then the rotational inertia is going to be greater as well. Okay, for example, okay, for this tightrope walker, usually, you know, he's going to, if without this rod, he's easy to rotate. He's going to be much easier to rotate, to fall. But instead, if he carries a long pole that extend rotational inertia, actually extend the mass distribution. So you can see here the mass distribution is further away. Okay, so then it's going to make the rotational inertia bigger. When the rotational inertia is bigger, then it's going to be harder to rotate him. Okay, so when he's at rest, so if the rotational inertia is bigger, so it's going to make it harder to rotate him. So it's going to make him harder to fall. Okay, so it's going, or in other words, it's going to be easier for him to stay on the tightrope. Similarly, over here, you have pencils like this, right? So like marker here, if you rotate like this, or if you compare rotating like this, okay? So this is much easier to rotate than this one, okay? Why is that? It's because you can see here for this case over here, this is the axis of rotation. The mass actually is very close to the axis of rotation, so the rotational inertia is smaller. So when the rotational inertia is smaller, it's going to be easier to change its rotational motion. But when you have these two cases, okay, and then the axis rotation is here, so you can see the mass is further away from the axis rotation. So the rotational inertia is bigger. When the rotational inertia is bigger, and then it's going to be harder to rotate it. Rotational inertia depends on the shape of the object and its rotational axis, okay? So you can see, actually, I'm not going to ask you to calculate the rotational inertia for these objects, but this slide is trying to show you that for different shapes, actually they have different equations to calculate rotational inertia. Okay, but here in order to calculate rotational inertia for different shapes, we need to use calculus, but which we're not going to cover in our class. There are some actually examples from the textbook. I'm going to show you. So I'm going to ask you guys to take a look at page 138. Page 138, okay? So I want you to take a look at the first question here. Okay, the first question. Consider balancing a hammer upright on the tip of your finger. The head is likely heavier than the handle. Is it easier to balance with the end of the handle on your fingertip, with the head at the top, or the other way around? So what's the difference between these two cases? If you can take a look at these two cases. Okay, so this case, actually the head is on the finger. This case, the head is further away. So if you want to balance the hammer, you want to keep the hammer, okay, at rest. You don't want the hammer to rotate, right? So if you want to balance that, you want to make sure the rotational inertia is bigger. When the rotational inertia is bigger, it's going to be harder for the hammer to rotate. So which case has greater rotational inertia? Remember, rotational inertia depends on the mass, but in these two cases, the mass is the same. But also, rotational inertia depends on how far the mass is away from the axis rotation. So your finger point is going to be your axis rotation, but the head here is further away from the axis rotation. So for this case, this has greater rotational inertia. So when this has greater rotational inertia, it's going to be harder for this hammer to change from rest to rotate. That's why it's going to be easier to balance this compared to that. Okay, so if you look at the answer here, okay, stand the hammer with the handle on the fingertip and the head at the top is going to be easier to balance, okay, because it will have greater rotational inertia this way and be more resistant to a rotational change. Okay, so I wanted to take a look at this checkpoint explanation on page 138, okay, trying to understand the relationship between rotational inertia, how the rotational inertia depends on the mass, as well as depends on the mass distribution, and how the rotational inertia is going to relate to the change of the rotational motion.